Today I'll solve one fluid mechanics problem based on pump. Here I'll calculate pressure difference across the pump. Now here is the problem statement. A pump is used to transfer a liquid specific gravity, that is 1.75, from a storage tank through a 6 cm diameter steel pipe where the flow velocity is 1.5 meter per second. So here this is the storage tank, and from that pump is pumping the liquid and it will reach to the discharge tank or stop tank. So this pipe diameter is 6 cm and velocity is 1.5 meter per second. So that is the case. That pump discharges the liquid through a 4 cm diameter pipe to an overhead tank with a discharge point located 12 meters above the storage tank's liquid surface. So this is the storage tank liquid surface. From here to here, that distance is 12 meter, and this pipe diameter in this discharge pipe diameter is 4 cm. The total frictional losses in the pump system are amount to 6 meter, means HL is 6 meter. If the pump operates at an efficiency 65%, calculate the pressure difference maintained across the pump. Means we have to calculate pressure difference between this 0.1 and 0.2. So now I have to solve this problem. So first, given data, specific gravity is given 1.75, diameter of inlet pipe of the pump, so that diameter is given 6 cm. So this diameter that is given 6 cm, and diameter of the outlet pipe, so this diameter outlet pipe diameter is 4 cm. Flow velocity at inlet at 0.1, so that is given, this 0.1 means inlet velocity is given, that is 1.5 meter per second, and height difference means from the surface level to this level discharge point, so that is 12 meter, and total frictional losses from here to here due to this pipeline, so that is 6 meter, and pump efficiency 65%. Now first we have to calculate what will be the velocity in this pipe, because velocity this pipe we know that is 1.5 meter per second. So velocity will be 4 cm pipe, we can easily calculate by using continuity equation. So inlet and outlet velocity at the point 1 and 2, using continuity equation A1 V1 is equal to A2 V2. So diameter of the inlet pipe D1 is given 0.06 meter, diameter of outlet pipe that is 0.04 meter, means 4 cm, that is 0.04 meter. V1 is given 1.5 meter per second. The cross sectional area for A1, so that inlet pipe cross sectional area is a pipe D1 square by 4, that is 0.002827 meter square, and outlet pipe cross sectional area pi D2 square by 4, that is 0.001257 meter square. Now using the continuity equation to find V2, so V2 will be A1 V1 by A2. So A1 is 0.002827 into V1 1.5 and A2 0.001257. So after doing the calculation, V2 will be 3.375 meter per second, means outlet velocity is 3.375 meter per second. Now here I am applying Bernoulli's equation correctly for the pump system between point A and B. So point A and point B, I am using the applying Bernoulli's equation. So we know that PA plus half rho VA square plus rho G ZA plus rho G HP plus PB plus half rho VB square plus rho G ZB plus rho G HL. Now PA and PB pressure at point A and B. VA is 0 because here there is no velocity. Velocity at the surface negligible. VB 3.375 meter per second. Outlet velocity we already calculate, so that is 3.375. Height difference ZA and ZB, that is 12 meter, and HP is the head added by the pump converted to the pressure. So HP is the head. HL is the 6 meter frictional head losses converted to the pressure. Now here that PA and PB both points are open to atmosphere. So PA is equal to PB and VA is equal to 0 and ZB is equal to ZA is equal to 12 meter. So P and assume PA is equal to PB, both point exposed to the atmospheric pressure. So cancel out the common factor or also P. So this term will be cancel out. This term will be cancel out. Okay, and then we will have that G HP, or we have cancel out this common term. Okay, so now we have GHP half of VB square, okay. So here this VA is equal to 0 and plus GZB minus ZA plus GHL. So now HP will be half 2G VB square plus ZB minus ZA plus HL. Now plug all these value. So we know that V2 is 3.375 meter per second, G is equal to 9.81 meter per second, Z2 minus Z1 is 12 meter, HL is equal to 6 meter. After plugging all this value and doing the calculation, so HP will be 18.581 meter. So now from here that adjust pump efficiency. So given pump efficiency eta is 65%, so 0.65. The actual head at the pump must be generated as HP actually is HP by eta, so that is 18.581 by 0.65, so that is 28.587 meter. So after getting that, so now we apply Bernoulli's equation, this point and this point, 1.1 and 0.2. So same equation, so P1 plus half rho V1 square rho G Z1 plus rho G HP actual, because we have to calculate the pressure difference between 0.1 and 0.2. Okay, so rho G HP actual, P2 plus half rho V2 square plus rho G Z2. So we know the velocity, okay, we know HP, okay, and here Z1 and Z2 we can assume both are same height, so Z1 and Z2 will be cancel out, okay, and the density we know, V1 square we know. So from that we can, and HL here no, and also assume no frictional losses, so HL is equal to 0. So ultimately so we have the pressure difference across the pump is P2 minus P1 rho GHP actual plus half rho V2 square minus V1 square. So rho is 1.75 into 1000, that is 1750 kg per meter cube. V1 we know 1.5 meter per second, V2 we know 3.375 meter per second. Now pressure difference across the pump is given by, so we plug all these value. So here rho 1750, G is 9.81, P actual 28.587, half then 1750 multiplied with that V2 3.375 whole square minus 1.5 whole square. So now P2 minus P1, so this total will be 490,767.3225, and this after doing the calculation, that is 7998.0469 Pascal. So finally if we add, we will get 498.77 kilopascal. So thus the pressure difference across the pump is approximately 498.77 kilopascal. Means pump will develop this pressure 498.77 kilopascal from this. So pump will develop 498.77 kilopascal. So that's it. Thank you.